Awesome. So I think I'm going to get started here. So thank you everyone for joining me today. My name is Wyatt, and I'm a software engineer here in the Next.js team here at Vercel. Uh, Partial Prerendering is an experimental rendering feature that we announced at last year's Next.js Conf. I've only been on this team for about 2 years now, and I've spent about half of that time leading its development. We're going to be taking a deep dive today into how it works and how it impacts site performance. It's changed a lot since we've initially announced it, so I'm pretty excited to share with you how it works. If you have any questions over the course of the webinar, just leave them in the chat. We'll be able to get to them at the end, ideally, if you have some time. First, we'll define the metrics that we use to measure site performance, core web vitals, and how they guide our efforts in optimizing the user experience. Next, we'll discuss how Next.js renders pages today, what I'll refer to here as traditional rendering. I'll break down the limitations of these methods and why balancing speed and functionality is a persistent problem for developers. This will also then lead us into partial pre-rendering, and we'll cover how it works, what changes we've introduced since last year. We'll also cover the new async request APIs that were announced with Next.js 15 and explain why they were needed, as well as covering how to identify static and dynamic content and to strategically use suspense boundaries and use the fallbacks. Looking to the future, I'll touch on some of the planned improvements that we're making for PPR. Let's get into it. First, let's talk about core web vitals, what they are and how they measure application performance. Core Web Vitals describes a series of metrics that provide us with a number that we can use to evaluate the experience of our users. The metrics that make up Core Web Vitals are the largest contentful paint, interaction to next paint, and cumulative layout shift. Each of these can be measured and include target values that help developers quantitatively measure how their applications perform. Today, we're only going to really be focusing on largest contentful paint as it's the most drastically impacted by partial pre-rendering. First, looking at one of the components of the largest contentful paint is the time to first byte. This is measured from the request start until the first byte of the HTML document is received. That's a really important metric as it's often associated with the server speed. It's also impacted by every layer of the network stack between the user and the server. The more layers that we have to traverse, the slower this metric gets. Next, we have first contentful paint. This metric also is measured from request start, but finishes when any part of the page's content is rendered on the screen. This is very important as well as it's associated with the user's perception of the loading speed of the page. If the time to first contentful paint is too high, a user may think that the page is broken. Finally, we have the broader metric, largest contentful paint. This is also measured from request start, but it finishes when the largest visible element is rendered on the screen. This includes any time it takes to unload the current page, set up connections, perform redirects, and the actual time to first byte metric of the HTML document. It's considered good to have a value that's less than 2.5 seconds, but honestly, that's a really long time. If users had to wait that an order of seconds, they might find another site to visit. And ideally, you should be targeting a number that's far lower than that, something in the realm of a few hundred milliseconds. So with that understanding of core web vitals, let's discuss the challenges we face with traditional rendering approaches. In web development, as this isn't isolated to Next.js, we typically encounter two different rendering strategies, static and dynamic. Static rendering is fast, but lacks request data. This includes single-page apps. Dynamic rendering includes request data, but can be slow due to server response times. This leads us to a critical question. How do we balance the speed of static and the functionality of dynamic rendering? Each of these has their own pros and cons, and choosing between them is often critical to an application's performance story. Static rendering is known for its speed, where we can deliver the entire page from the edge. We avoid a trip back to the origin to get the initial HTML to send it to users as fast as possible. Static rendering, however, lacks the ability to read request data, requiring any dynamic data to be retrieved using client-side requests, resulting in expensive round trips to the origin. In Next.js, when you want to access request data, you call one of the data request APIs, like cookies or headers. These are only available in server components, and once called, the entire page is marked as dynamic and opted out of static rendering. With dynamic rendering, the request data can be accessed, and the HTML can be rendered server-side. This also means, though, that users are left waiting as the network has to reach all the way back to the origin in order to get the first byte of HTML. This does mean, though, that we can retrieve the data needed to render our pages faster, reducing expensive round trips. Both of these approaches are what Next.js does today. But I've talked to you for a little bit now with a bunch of slides. And if you're anything like me, you probably will appreciate some practical examples of what constitutes a static and dynamic page. So I'm going to switch over to our little demo. Give me just a second to get that all shifted over. Awesome. So this is EcoStore. It's an eco-friendly e-commerce store. It's a mouthful, I know. The name's still in progress. This represents a real-world app that has a lot of dynamic content that needs to be fetched from the server. For example, we store in the cart all the information of how many products the user has queued up, and we store that as a cookie. This means that that we actually need to read request data in order to display the cart to the users, which presents a problem for developers. Do we read the cart data via a fetch call on the client and let the page render statically? Or do we read the data on the server and let the page render dynamically? Thankfully, today for you here, I've implemented both. To understand what an application would look like with a client-side fetch, let's take a look at the cart component. So the static cart component, taking a look at it here, uses SWR to fetch the cart data. SWR is a library that lets us optimize making client-side fetches and makes requests to the browser and handles revalidation. But we have a problem. But because this code only runs in the browser, it has to wait until the page is hydrated before it can fetch the data from the server. This means that the cart will have to be empty until both hydration is finished and the fetch is done. It also has the longest distance to travel from the browser to the server, increasing the latency. We can't rely on a CDN here because we're reading the request data and not displaying static content. We did, however, load the static page faster in the CDN, so I was able to preload the JavaScript, CSS, and fonts for the page. Now let's take a look at the dynamic version of this. So we have this suspense boundary that wraps the dynamic cart component. Taking a look at dynamic cart, it's an async component, uses a wait. Let's take a look at get cart. We can see in this implementation here, get cart is wrapped by the React Cache API and also calls cookies. So now that we know that it calls cookies, we can read the request data server side. But what we do in traditional rendering, as we notice, is that when we call await cookies, it's going to mark the entire page as dynamic and bail it out of static generation. This means that every time a user wants to visit this page, the server has to run before it displays even the first byte of HTML. So I'm going to switch back over to the slides. So the challenge here right now is, how do we balance these two approaches? How do we achieve the speed of static rendering while retaining the personalization of dynamic rendering? This is where the limitations of traditional static rendering methods become pretty apparent. Developers are usually left here now having to choose between speed and functionality. These challenges highlight the problems that partial pre-rendering aims to solve, combining both the strengths of static and dynamic rendering methods. We'll go back a little bit here. Enabling partial pre-rendering is as simple as adding the experimental PPR flag to your Next.js config. Once enabled, pages will be rendering using the new rendering pipeline. So what partial pre-rendering does is it enables us to generate a static shell at build time, which is served directly from the edge to browsers, while a request is sent back to the origin to complete the dynamic render, which is then streamed on the response back. So it's really composed of these two parts. Getting the static shell to users early is critical, as it allows resources such as JavaScript, CSS, and fonts to begin preloading as early as possible. But how does Next.js do it? We use React. During build, we call the React DOM pre-render API. It produces two parts. The first part here, named the prelude, is the static shell. Secondly, we have the postpone state. The postpone state here is just a JSON object. It's serialized and then sent back to Next.js during the dynamic resume render. React uses this postpone state as a reference as to what was included in the static shell, allowing React to only send down the dynamic parts. The React DOM API resume creates a stream that we attach to the static shell stream that started from the edge. The timing of this part is really critical, as it means that at the same time that we've started to serve the static shell to users, we're also kicking off the dynamic invocation of the origin, saving precious milliseconds. This means that as the browser is already downloading static resources that were hinted from the static shell, either via link headers or tags, we're already invoking the server at the origin to render the dynamic parts of the page. Thanks to React streaming, these pieces are sent in and swapped with their suspense fallbacks. This means that we get all the dynamic parts of the page, even before Next.js is hydrated. The difference from traditional rendering methods here is that when we detect request data being accessed, we don't bail out of static rendering entirely. Instead, we just trigger the fallback at the nearest suspense boundary. In this example, cart accesses request data. As a result, the cart skeleton will be included in the static shell, having the cart component streamed in via the dynamic resume render afterwards. If no component on the page accesses request data, it would render the entire page during the pre-render. No need for the dynamic resume render. You get to just write React. The question then is, how do we detect when you try to access request data? This has been a problem that the team has been working on for over the past year. We made some changes. I'm really excited to share that journey with you here. Last year, when we introduced partial pre-rendering, we took advantage of the React Unstable Postpone API. This API threw an error when invoked and was used by Next.js when you called functions like cookies or headers during pre-rendering. The error was then caught by a surrounding suspense boundary. We assumed this approach would work really well, nearly as well as other APIs we have today, like not found or redirect, which also use errors to communicate user intent. The problem we noticed, though, is that when users accessed external APIs, like database drivers, is that they weren't expecting these operations to throw. This triggered issues like entering retry loops, and the code assumed that it was a fetch failure and tried to recover with a retry. Additionally, user code is at risk too. What's the first thing you might think of doing when you see an await in your JavaScript code? Probably wrap it in a try-catch block so that you can ensure that any rejected promises are also correctly handled. This led to the introduction of the unstable rethrow API. This, in this case, was needed, as it provided a mechanism for users to safely rethrow framework-generated errors. This let users write try-catch blocks to handle unexpected errors, but not interfere with the framework errors that were used to communicate with it. This solution introduced a new problem, though, and required developers to remember. If there's one thing developers are really good at, it's being lazy. Or maybe that's just me. We don't want to remember stuff. We Google everything. If remembering things were easy, we wouldn't need languages like TypeScript that warned users when they forget a field. With these types of errors being thrown all over users' application, we were left with no consistent or reliable way to warn users that they needed to rethrow framework errors. Suffice to say, we had a few problems with the design. What we needed was a way to suspend the processing of user code when they tried to access request data. Errors that seemed like a logical choice, but the trade-offs of try-catch blocks meant that these signals that were meant to inform Next.js about request data being accessed would be unreliable and possibly lead to longer than expected build times due to the retry logic. But if we can't throw an error, then what primitives do we have left? The answer? Promises. Developers are already really adept at managing promises. And with the advent of React Server components, for the first time, users could write async components, allowing data fetching to be co-located, all while using native APIs that we're already familiar with, such as fetch. So let's take a look at our request APIs. We need to make these functions not just return promises, but we also needed to have it not be an ordinary promise. This particular promise would never resolve during a static pre-render. We had to change these request APIs that were previously being synchronous to being asynchronous. This meant that we also deprecated the previous unstable no-store API in favor of the new await connection API. Now, this works well for existing APIs like cookies or headers, but what about other I/O? We definitely don't want to patch every single API. To solve this, we can take advantage of an already built, tried and true scheduling mechanism, the Node.js event loop. Now, this is where things get a little bit technical, but you didn't join this call for not technical discussions. And I'm only going to nerd out for a few slides, but I'll finish it off with a demo just to bring you all back. So Node.js is single-threaded, which means it can only run one block of synchronous code at a time. This means that when it needs to perform tasks like I/O, it has to offload them to native code. An example of this is when we await a fetch or register a callback for reading a file. Next.js can take advantage of that fact. As I/O is non-deterministic, I/O that is non-deterministic can't complete in the same task. And this allows us to do something quite novel. First, we schedule a task using setImmediate to pre-render the application, and then synchronously schedule it to abort in the next task. Node.js will perform all the microtask queue elements before moving on to the next task, so that all the microtasks that have already resolved promises would occur before the next task to abort it run. This is really the secret sauce of how Next.js does it. I literally copied this from the Next.js source code a couple of days ago to make the slide. But you must be wondering, how do you include external data in your static shell? Data from your CMS may require a fetch to retrieve, and it certainly won't complete within a single task of the event loop. What we do is we identify any and fill any cacheable entry, which are those annotated with Next.js cache APIs, like useCache or even unstable cache. We do this during a prospective render prior to pre-rendering. This is where we perform a render, letting it fill each of the caches as all the I/O occurs, and then discard that render result, because that particular render was only used to fill the cache entries, so that when we perform the actual pre-render, it's already available and can be resolved within the first render task. In this example, getData calls fetch, which is not cached. As a result, the attempt to render component is aborted because the fetch for the data didn't complete within the first task. This causes the skeleton component to render instead. We refer to these pages as being partially static. They require the additional resume render in order to stream in the dynamic parts of the data. What if, however, we wanted to include the data in the static shell? Well, this is where we can take advantage of the cache APIs. Adding useCache here allows the promise for getData to be evaluated within the prospective render. This means that when we perform the actual pre-render, the cache data is already available and is able to resolve within the first task. This page is now fully static. These static pages can be served from the edge cache as they don't require an additional resume render. To enable this new mechanism for detecting request data access, you need to add the dynamic I/O true flag to your Next.js config, along with PPR true. I wanted to use a special callout here for APIs that access path name information. In traditional rendering, when a page is requested that we haven't pre-rendered, such as a page with dynamic path parameters, we'd either have to generate this page at runtime, blocking the browser until the page is rendered, or dynamically render the entire page. Onwards to partial pre-rendering, we have a solution. We can perform a pre-render at build time to generate a fallback static shell. This is similar to what we had with the pages router with fallback true. Because we made the params prop a promise in Next.15, you now have to await it. When we resume these fallback shells, we provide the full path name, enabling those pages to render as fast as static, even if you've never visited them before. You get all of these benefits, all from adding suspense boundaries to your application and enabling partial pre-rendering. So let's do that. Let's take our eco store from before and configure it to take advantage of partial pre-rendering. Give me just a second to switch to the other demo. Awesome. So back to EcoStore. Let's take the dynamic version of this page over here and configure it to work with partial pre-rendering. The first thing we need to do is update our Next.js config file. I'm going to go over here, add a new PPR flag, add the dynamic I/O flag, and hit save. Now, let's take a look at the actual page itself and see what we need to change. Looking at dynamic cart, we notice that it uses an await, calls getCart, again, which calls cookies. But what is partial pre-rendering? What has it actually done, enabling this for us here? Well, It means that when dynamic cart tries to access request data, it's going to fall back to the fallback shell using the surrounding suspense boundary. But we've already wrapped it in suspense. To support dynamic API access and using dynamic rendering, that was something that we've already recommended you do. So this component is actually suspended to create a dynamic hole. And because we've already wrapped it, it's already finished. Taking a look at product details, it receives params, which is a promise that resolves to the ID of the particular product we're loading. And if you see inside the product details page, it's also just awaiting props. Awesome. Looks like we're pretty good here. So again, what did we have to add? Turns out it was just that configuration. Because we were already following the rules of React and our recommended data fetching patterns, we didn't have to make any changes to the application code. It just worked. Let's switch back to the other slides. So not only was this easy for us to add, but it also presents a great experience for your users, as they're able to now experience the site arriving fast and with well-designed fallbacks for data. We simply had to use the language of React and compose the components. For those of you tuning back in, it means that if you're following the patterns we recommend for building React Server components, you're already ready for partial pre-rendering. Suspense is our mortar, creating stable boundaries for the dynamic parts of the page to stream in. Thanks to partial pre-rendering's hybrid rendering approach, we're able to serve the static shell to users fast from the edge, minimizing the time to first byte and first contentful paint. And thanks to us kicking off the dynamic render at the same time, we're streaming our static data, we're able to minimize the time it takes to load our request data, thereby minimizing our largest contentful paint. Partial pre-rendering really is the future of Next.js and the app router, but we're not done yet. Today, both of these flags are required to take advantage of all these features. While we're not planning on bringing partial pre-rendering out of experimental for Next.js 15, we are planning on eliminating the dynamic I/O flag. This soon will be the only way partial pre-rendering performs. I've also talked a lot today about the streaming nature of partial pre-rendering and its novel approach that lets us minimize round trips made by the client to optimize the loading experience. We decided to solve the hard problem first, allowing users to maximize their experience for their users. The problem today is that the single stream approach is only currently supported on the Vercel the problem today is that it's just supported in the Vercel platform, or that $5 VPS. That's right. Self-hosting also supports streaming the dynamic response along with the static stream. What it lacks support of today is support for other CDNs, but I have some other good news. We are planning on adding CDN interoperability support. Once PBR has been marked stable, we're planning to make this feature compatible with other CDNs. I don't have a lot of details to share yet, but we're planning on enabling the additional pre-render and resume mechanisms that would allow a CDN to serve and cache pages using partial pre-rendering. So in conclusion, partial pre-rendering represents a significant advancement of application rendering strategies, offering the dynamic at the speed of static. Understanding how PPR works may not have been necessary, but I hope you enjoyed the deep dive into the engineering behind its development. It's really been a passion project of mine for the past year, and I'm really excited to have been able to share it with everyone. So thank you. Now, we do probably have a little bit of time, so I can answer a few questions that have popped up in chat and see if I can answer some of those here. I'm also going to start a session feedback little quiz here, so if you have a chance to answer that, I'd recommend that as well. So I had the first question here was around if there's any difference if you're using Bun or Dino instead of Node. And I'd say no. In order for different runtimes to be compatible with existing JavaScript code that also takes advantage of the event loop, it's also going to be probably following the same mechanisms and scheduling patterns that is used today by Node.js. So I'd say that in both of these scenarios, it's using the same patterns. Let's see. Moving into another question here. So a question around PPR will work in self-hosting and standalone mode. The answer is yes. Is that like if you self-host this in a Docker container on a $5 VPS, it'll all work with partial pre-rendering. The only thing, of course, that it doesn't do is there's no edge component that sits in front of the application that fronts all of that. but it will be able to serve all of the static parts off of the disk cache before it goes to evaluate the application code. So that still saves you a lot of time and a lot of CPU resources and gets that content to users even faster. I do have the demo for that. The slide, the repository for the demo. I'll drop that in chat for y'all. How do I do that? Let's see. Chat. Awesome. Great. So another question here is, how did the React 19 compiler impact some of these? So I'd say that in a lot of cases, the compiler is sort of going to work in parity together with this. What the React compiler does is it optimizes the structure of inside components and how they're all structured, but really partial pre-rendering is building on the foundations of React using React. So we're actually still everything really works well together and all connects well together. So there shouldn't be any impacts there. Let's see if there's another question. Yeah, so the question says, if I understand correctly, if I use suspense, the Next.js server pre-renders the suspense fallback and caches it. So it's not exactly that, it's always going to perform or cache the fallback. It's going to attempt to render what's inside the suspense boundary. And if it's able to resolve within the first task, then it'll actually use what's inside the suspense boundary. It's only going to render the fallback if it's unable to resolve what's inside, like the component's unable to complete rendering within that first task. Sort of the magic of dynamic I/O in this case here. Let's see. And the one thing that we're also trying to work on still is the streaming metadata. So that's something that we're currently working on a bit here. So that generate metadata tags are things that currently we don't support suspense inside the head. And that we're trying to work on improving some of those stories. And that's a part of making PPR more stabilized. And I think that's about all the time we got left for. So if you have any other questions, feel free to send me a message over on Blue Sky. And I think we'll be dropping some other links later. So thank you very much, everyone, and have yourselves a good day.